Hello everyone, I am KVMS Lokesh from CSE branch. Today I would like to explain about the random variables topic in probability and statistics. Random variable plays a key role in probability and statistics for analyzing the statistics using probability. Today I would like to explain it briefly. Now, Now coming to the definition, a random variable is a variable whose value is subject to chance or a randomness. It is often denoted by a letter such as capital X or capital Y. In our day-to-day practice in probability, we may all have came across the situations in which the random variables may are in need, but one may not be aware that the random variables are used in that kind of situations. Now let us see some examples in which random variables are included. Some examples of the random variables that includes the outcomes of coin flips, the number of heads in a sequence of the coin flips, the sum of two dice rolls, the height of a randomly selected person, and the temperature on a given day. These kind of situations are the situations in probability which may include the random variables purpose. Now, what is the importance of random variables in these kind of situations? Let us have a look. Random variables are important in statistics and probability theory because they allow us to quantify and analyze the uncertainty. By studying the distribution of a random variable, one can gain insights into the behavior of a system or process. It means the random variable describes the behavior of a system or a process. For example, if you throw a pair of dice, there may be certain outcomes, but one may not guess correctly that this is the exact outcome. But using the random variable, one may describe the behavior of the process like this. Such outcomes may occur and these may not occur, which lies the uncertainty in the range of 0 and 1. So one may understand that the random variables are very important to quantify and analyze the uncertainty of certain probability events and trials. The random variables are generally classified into two types. They are discrete random variables and continuous random variables. Each have their own importance in the analyzing the probability and uncertainty in the statistics. Now let us have a look about each one of them. Discrete random variable. A discrete random variable is a variable that can only take on countable number of values. Its probability distribution is described by a probability mass function which gives the probability of each possible value. Generally, a probability mass function which describes the each value at the of the probability which may lie between the 0 and 1. It gives the each possible value of a probability uncertainty event. Probability mass function. The probability mass function of a discrete random variable x is denoted by p of x. A probability mass function of a discrete random variable must satisfy the following properties, that is, p of x greater than or equal to 0 for all of x. It means that every outcome of an uncertain event should be greater than 0. It means there should be no impossible event. That means its uncertainty should be greater than or equal to 0. And sigma p of x equal to 1, where sum is taken over all possible values of x. It means the second condition is nothing but the classical definition of probability. It is the sum of all probabilities of the uncertainty event should be 1. Now let us have a look of examples of discrete random variables. Some examples of discrete random variables includes the number of heads in a sequence of coin flips, the number of arrivals at a service desk in a given time period, and the number of defective items in a batch of products. These all discrete random variables may include its applications into several types of distributions such as binomial distribution, Poisson distribution, and normal distribution, etc. For example, we have seen the examples of discrete random variables, such as if the number of heads in a sequence of coin flips follows the binomial distribution, and number of arrivals at a service desk and the number of defective items in a batch of products follows the Poisson distribution. These type of discrete random variables are useful in analysis of distributions, several types of distributions, and normal distribution also. This is about discrete random variables. Now let us have a look at continuous random variables. Continuous random variables. Continuous random variable is a variable that can take any value within a range, that is, uncountably infinite number of values. Its probability distribution is described by a probability density function, which gives the density of probability at each point in the range. A probability density function is a continuous random variable x is denoted by f of x and satisfies the following properties. That is, f of x greater or equal to 0 for all x. It means the uncertainty event which may be performed as a trial or error may be an impossible event or not. For all x, it means every event that occurred may or may not be impossible event. And sigma f of x dx is equal to 1. It means the integral is taken over the entire range of x. It means the sum of all probabilities of the x is equal to 1. Now let us take the examples of continuous random variables. Some examples of continuous random variables includes the height of a randomly selected person and the time between a successive arrivals at a service desk and the amount of rainfall in a given area. Like the discrete random variables, continuous random variables also follows some distributions such as normal distribution, exponential distribution, binomial distribution, etc. Generally, the continuous random variables falls under the category of normal distribution and exponential distribution, whereas the discrete random variables follows the binomial distribution and Poisson distribution. As we have seen the examples, height of a randomly selected person follows the normal distribution and the time between the successive arrivals at a service desk follows the exponential distribution. In rare cases, such as in daily lives, the amount of rainfall is calculated in a particular area. This type of calculation requires the gamma distribution. So the general differences between a discrete random variables and continuous random variables is discrete random variables accepts only a finite number of values such as 1, 2, 3, 4, that means a countable number of values, whereas continuous random variables accepts the infinite number of variables, that means it accepts each and every value given in the range. This is the major difference between discrete random variable and continuous random variable. For easy identification, a discrete random variable follows the probability mass function and a continuous random variable follows the probability density function. Now let us have a look about expectations and variance. Through the discrete random variables and continuous random variables, one may calculate the mean and variance of the distribution. The properties of expectation and variance may be included as linearity of expectation, that is, expectation of ax plus by is a into expectation of x plus b into expectation of y for any constants a and b, and the x and y are generally random variables. Variance of a sum var of x plus y is equal to variance of x plus variance of y plus 2 convergence of x y, where convergence of x is the covariance between x and y. Independence. If x and y are independent, then expectation of xy is equal to expectation of x into expectation of y, and covariance of x comma y is equal to 0. The expectation and variance are very helpful in calculating the mean and the deviation from the mean. The expectation and variance have very many daily life applications. These are useful in calculation of central tendency and dispersion values. The interpretation of expectation and variance. The expectation and variance of a random variable can be interpreted as expectation of x represents the center of the distribution of x. Variance of x represents the spread or variance of distribution of x. It means generally expectation refers to the mean value. It is nothing but a central tendency value. Variation of x, which is the square of the dependence of x, it represents the spread or variance of the distribution of x. It generally distributes the standard deviation over the distribution. Now, moving on to joint distributions. A joint distribution describes the joint behavior of two or more random variables. For two random variables, x and y, the joint distribution is described by a joint probability mass function or joint probability density function denoted by p of x comma y or f of x comma y respectively. It means in some certain cases such as rolling of two certain dice in 3 boxes reflects this situation. Calculation of marginal distributions. The marginal distribution of a single random variable can be obtained by summing or integrating over the other variables. It means the general properties that are used here are the summation and integration. For example, a marginal probability mass function of x is given by p of x equal to sigma p of x comma y over all possible values of y, and the marginal probability density function of x is given by f of x is equal to integral f of x comma y dy over the entire range of y. It means y describes the infinite range that is continuous random variable, and x is a dependent variable which describes the discrete random variable. It holds only a finite number of values. It means two types of distributions are combinedly active. This is nothing but a joint distribution. Calculation of conditional distributions. The conditional distribution of one random variable gives the value of another random variable that can be obtained by dividing the joint distribution by the marginal distribution. For example, the conditional probability mass function of y given x is equal to x is given by p of y by x and p of xy given p of x. It means the conditional probability density function of y given x is equal to x given by f of y by x and f of x comma y given by f of x. This is nothing but a conditional distribution function. It means the outcome of one distribution function depends on the another distribution function. It is nothing but a conditional probability. As we have seen that the random variables have many applications. That is, they are used in analyzing the statistics using probability and may fall under the distributions such as normal distribution, binomial distribution, Poisson distribution, gamma distribution, etc. Now let us have further look on the applications of random variables. The random variables are used in statistical inference, such as random variables plays a central role in the statistical inference, which is the process of making inferences about a population based on a sample. Some examples of statistic inference using random variables includes the hypothesis testing, for example testing whether a coin is fair or not, and conducting the confidence intervals, for example estimating a population mean or proportion, and regression analysis can also be made using the random variables. Regression analysis is generally used in the modeling the relationship between two or more variables. This is mainly based on the random variables such as discrete random variables and the continuous random variables. And the use of random variables in simulation and modeling is very critical. The random variables are very important in simulation and modeling, which involves the using of computer programs to simulate the behavior of complex systems. Monte Carlo methods, which involves the generating random samples from a distribution, are a common technique for simulation and modeling. We have some real-world applications for random variables such as including in queuing theory. Queuing theory generally is based on the modeling the behavior of customers waiting in line. Financial risk analysis, modeling the behavior of a stock prices, and machine learning. These are the real-time applications of the random variables. The real-time applications may also include the modeling the relationship between features and outcomes in a dataset, which may be used in the programming languages. These are the applications of the random variables which may generate the scope for the future purposes. Now, finally, to sum up, in this presentation, we have defined random variables and discussed their importance in the statistics and probability theory. We have also discussed the discrete random variables and continuous random variables and their usage and which categories they may have fallen, such as normal distribution, binomial distribution, gamma distribution, etc. And what we have expected from the expectation and variance, such as for calculating the standard deviation and mean of the given distribution, and the joint distributions, which includes the two types of distributions such as binomial distribution, normal distribution, which may include the combined features of discrete random variables and continuous random variables, and some real-time applications and theoretical applications of the random variables. I have given a glance about the importance of the random variables. Random variables are a fundamental concept in statistics and probability theory, and a thorough understanding of them is essential for many areas of science such as data science and machine learning, which may be useful for generating a further scope in the engineering. Thank you for listening to the presentation.